So good morning and welcome to this second webinar of our six-pack series, SmartEnergy. I am very happy to welcome you this morning. We will maybe wait one more minute for people to join us. So we are here all together for the whole morning, at least 2 hours, and then you will have the opportunity to attend B2B meetings on a dedicated and separate platform. We will give you a bit of information in a couple of minutes. So maybe we can start. Good morning. My name is Laure Quintin. I'm head of European projects in Minalogic cluster, digital cluster in France, Auvergne-Rhône-Alpes region. Together with my colleagues from Tenerrdis cluster, we designed this webinar series dedicated to smart grids in our region, Auvergne-Rhône-Alpes. Some of you might have already participated to the first workshop webinar last week. Today, I am very glad to present you the overall program dedicated on smart grids as key elements of the French electricity system. So we have today 6 great speakers presenting you a large and future views on the French electricity systems. And you will also be able to attend a matchmaking session where you have still now the time to register for and prepare your B2B for the end of this morning. So as you noticed, you're here again only as a listening mode, but do not hesitate to ask your questions in the chat. After every presentation, we will take 5 minutes to ask your question. I will read them for our speaker, and we might have a short exchange before moving on to the next presentation. So very briefly, for those who weren't there, this webinar series is part of a European project where 6 European clusters joined their forces to propose, let's say, a joint support on industrialization and market access to their companies or members. This, of course, can also interest other members of our and partners of our community. The idea is to foster and enhance the integration between the energy sector and the digital technologies. And we address in the project topics such as smart building, sustainable mobility, smart industry, energy management, or smart grids. The workshop or the seminar series here is about smart grids. So we propose such webinars informing and training a bit our communities to these topics. And we would like also to promote and enhance the exchange between our communities. And this actually takes place in the what we call cluster exchange program, where we were supposed to have visits but because of the pandemics, we decided and proposed now virtual exchanges on a B2B platform. So after each webinar of the series, you can meet exactly the participants. So our colleagues in Europe do the same on other topics, and you can still, I think, have one chance to listen to speakers from Italy about hydrogen technologies. Our Belgian colleagues present more their energy communities in Belgium, and here smart grids. More to come, but we don't have any information yet, is about smart buildings in Hungary. So just here, the overall program of our series. So we are here on the second webinar on smart grids as key elements of the French electricity system. Just mark in your calendar the 4 next meetings and dates every Thursday, same hour. Matchmaking session is here again for you, the link to register. You can do it until the last minute. Just very quickly create your account and select your partners you want to meet in short B2B online meetings. So it's okay from now for me. Let's give the floor to our presenters today. And I'm very happy to and glad to welcome our first speaker, Noureddin Said from Grenoble ENP Engineering School, and he will present us his big picture of smart grids in France. Mr. Said, the floor is yours. Welcome. I will present your slides for you. Just make them run if you want.
Perfect. Do you hear me? Hello, everyone. Do you hear me?
Yes, we hear you.
Okay, perfect. Thank you. So good morning, everyone. And it's my pleasure to be here and share with you some of our thoughts on what's going on in terms of smart grids in France. And this is a general presentation that introduces what's going to be discussed actually during the day. So the big picture of smart grid in France. First of all, well, smart grid has been around for about 2 decades now. So a lot of things have been done, not only in France, but worldwide, obviously. And it has been driven by different drivers, such as societal, economical, environmental, but also technical. And among all those stakes, I would say, there was this French energy transition law that gave some objectives that affected particularly the evolution of the electricity system in France, such as, for example, setting some objectives in terms of the share of renewable energy systems by a certain horizon, which is 2030, I would say, by reaching 40%, up to 40% of the electricity production, but also the reduction of the final energy consumption by 2050, or simply by setting also some objectives in terms of diversifying the electricity production by reducing, for example, the share of nuclear, which you may know has a significant share in France. So this is just to see how in France we have set some of those objectives that affect, again, the electricity sector. But if you look, I would say, worldwide, and consider some highlights in energy transition, the last years, starting from 2015 and even the 2020, actually were the warmest years ever recorded. The most cold was on 1909. And of course, what just said in terms of law. There was this energy transition bill and the COP21 that set the 2 degrees reduction in terms of temperatures, that also bring a momentum everywhere towards more renewable energies and so on. As a result, actually, we have seen that it has been around the average of $300 billion invested in renewable energy worldwide. And currently, we record something like 1,300 gigawatt on PV and wind worldwide, and with the objectives, or with perspective actually, that we can reach something like 2,000 gigawatt by 2023. So there is a very important increase, and the same thing also in terms of decarbonation, with the fact that we have seen the takeoff of EVs. EVs, for us, we see the EVs in its connection, or its connection, yes, and or its impact on the power grid, and then the evolution of the power grid in order to accommodate actually the electrical vehicle. And worldwide, actually, what's interesting is that we have seen over more than 300 million people have gained access to energy, whereas we know that just some years ago we have recorded between 1.5 to 2 billion people without access to electricity, and this access actually was made possible thanks to the decrease of the cost of those renewable energy, and then it was possible to supply those remote population. But definitely, the thing is that with those renewable energy, we've seen that we know that with the projection on 2024, the 2040 or 2050, we know that although we have those objectives of reducing the electricity, reducing the energy consumption, however, the electricity will take an important share, which means that if you can look here, the green part, which is the electricity share in the energy system, and that electricity share will be increased. I would say here that somehow the future will be electric. But anyway, the thing is that the electricity vector will represent a significant share in the overall energy system, and it can be seen also not only for this decarbonation and change in the usages, but also the electricity for digital that will increase, and also the consumption for EVs and so on. So, as a matter of fact, we have seen this the French evolution that you can see in terms of renewable energy sources, and currently, what's important, what's the message today is that just we have something like, of course, the end of 2020, the renewable energy sources represent something like close to 27% of the French consumption. But what's important is that we have, for example, just the wind and PV. Today we are about 27,000 megawatt, and 20,000 megawatt. It's not the number that's important. What's important is that if you consider just, for example, the distribution grid, and the distribution grid that represent more than 400,000 distributed generation units. And just keep in mind that some years ago, I would say maybe just less than 10 years ago, that was almost zero at the distribution grid, and now we are more than 400,000 distributed generating unit. In addition, if you just consider, for example, just before that, when we have a peak demand in France of about 1,000 megawatt, that it can be supplied, theoretically speaking, by 1,000 large generating units, for example, nuclear. Okay, 1,000. But here, from the 27,000 megawatt of PV and wind, this is just installed capacity. Doesn't mean that we do have it. So that means that for this 27,000 megawatt, we have them through a large number of units, which complicates, of course, the operation of the grid, given of this distribution nature of this distributed generation. And this movement, actually, this dynamic is actually worldwide. And you can see just underneath that this is the same worldwide, where you have the same evolution for wind and the same evolution for PV. Now, what's the impact here? What's the impact here on the grid? So this is just the picture, the overall picture of the grid. It's a pity. It's a little bit unfortunate because the fact that we're using this video tool, I cannot use the animation. Otherwise, you will see a nice animation here. But it's the tool, and I will work with it. So we have here this the grid with those two parts, the transmission and the distribution. So some years ago, as I told you, since we don't have that many generating units at distribution grid, the energy was flowing mostly on central generation down to the distribution grid with that was acting just as the delivery system, which means that it delivers actually the last kilowatt hours to the end users down in the feeder to the end user. But now, with those the development of renewable energies, having in mind that today in France, because this is the picture for France, nearly 95% of all these renewable energies are connected actually at the distribution grid. And this distribution grid, given the nature of the distribution grid, it was not designed to host that large number of distributed generation in this grid. And as a matter of fact, I mean, there are a lot of issues that happening, including, of course, reverse flows, but we have some positive and negative impacts. Some are positive, obviously, but most of them are negative. The fact that they are renewables, because the output, for example, I'll just show you later on that the output of those renewables, they are not traditional for the power system. Managing the assets, which means that for us, the power grid in France, in particular distribution grid, is where the average age is about 30 years. Is about 50 years. Well, when you compare it to the other power systems, it may look actually as young, but still, 30 years. We know that the failure rate is relatively constant for the first 30 years, and after 30 years, then it starts to change, and we can get more failures. And when we get both failures, then the cost of the failures is high, and it's less and less accepted by the people. And in addition to that, the operators, actually, that you will see the presentations after my presentation, you see that they are facing to fast evolution. And when we are used to have time to accommodate, for example, the interconnection of a large generating unit at the transmission grid today, at distribution grid, the rate of evolution is so fast that planning the grid evolution in order to accommodate all what's going on, particularly at distribution grid, is clearly challenging. Now, when you look, this is always what I like to show this slide and this picture, because it gives really the view on how the particularity of those renewable energy sources with respect to their output. So at the left hand side, you can see here that this is actually the power output of a wind farm in UK during 1 month, and the measurement was done with the sampling of 10 minutes. Every 10 minutes we were measuring, and you can see this high variability. Of course, we are managing today this variability with appropriate and good tools forecasting. But when the situation when we have a large volume of those renewable energy, having in mind that the pooling effect is not really effective for the wind generation, but the forecasting, actually, we know that even today sometimes the forecasting tools they may present about 50% of error, and this is extremely challenging. And the same thing on the right side here. This is also a PV farm, and the PV farm, which is about 4 megawatt in southern France on one day, that is quite favorable, and you can see the variability as well. And this is the high variability is mostly linked to clouds when they are crossing actually the PV plant, and you see also that we have this variability. And again, keep in mind that the pooling effect is not very effective in this situation. And when you add actually what's going on and what will going to happen with respect to the plug-in electric vehicle and the projection that we have, which means that we are, for example, just here you have the RTE projections where by the horizon of 2035 we will have between 9 to 16 million electric vehicle, and this also will be challenging, particularly if we associate those electric vehicle with fast charging stations, and then fast charging stations for the distribution grid may be challenging, and then it pushes actually towards thinking about more smart management for these issues, particularly for smart charging, because some of the experiment that was conducted in different area of the world showed that without some smartness in the management of those charging, actually the charging actually was added to peak demand in the system considered. So that definitely there is a need for this smart charging. Of course, the technology is right; they're here, but the question is definitely accommodating the fast evolution. The same thing also now, besides this variability, you have the technical impact of the distribution grid. I will not detail this here because they're a little bit more technical, where you have voltage challenges, voltage impact on the grid. You have technical losses on the grid. You have also harmonic at the secondary distribution, because some of the transformers we have seen failures, a lot of failures of transformers due to this harmonic caused by actually the inverters, low quality inverters. And we have solution. We know how to deal with the harmonies, but the question is again accommodating, of course, the fast evolution, determining where, and then who's going to pay the additional the initial investment. And one other thing which is on the overall grid we are concerned more and more is actually what is called the reduction in the system inertia. Where in traditional system we're used to have actually these large we call them synchronous generating units, which are actually rotating machines, and then the rotating machines. Actually, they provide also one thing, something that is interesting for the grid, particularly with regards to its stability, is the inertia. But as those kind of generating units are phasing out and they are replaced with those renewable energy sources that are interfaced with power electronics converters, I would say. And the effect of those power electronic converters is that now we don't have those. I mean, we are having less and less, particularly in small systems, less and less rotating machines, less and less inertia. And as a matter of fact, the system is more vulnerable to the different disturbances. What you can see here is the decrease in the inertia in the Danish system, for example. And here is the frequency response with respect to a fault in a small island. Obviously, it's not in the mainland, but you can see that this is without PV, this is 10% PV, and this is with 30% PV, when you can see that the escalation actually is going worse as we are going further in the rate of renewable energy sources interconnected to the grid through power electronics, the converters. So as a matter of fact, actually, we know that the power grid is already considered as the most complex infrastructure ever built by man already. And now with the given situation, with this evolution, is getting more and more complex. And the question is that how to deal with this complexity, given the fact that complexity for us means vulnerability and cost. So definitely we need to fulfill those changing needs, and they would say fast changing needs in terms of new usages, the position of the consumer as being an actor. All these issues relate to the renewable energy DG integration and how to manage the overall balance with the increasing uncertainties. And definitely we need more intelligence in order to actually optimize the cost to accommodating all those movement and all those changes. And whatever are actually the solution, the intelligence that we can embed in the grid, we need to satisfy three kinds of constraints. The first one is technological, because we need to build on existing assets. And some of the assets actually that we have in France, but the same thing in other areas in the world, they may have more than actually 60 years. We have only 30 years, but the average can be more 60 years. So it's challenging actually to couple very advanced technologies with very old technologies, and they have to work together. This is a constraint. The same thing in terms of maturity of the technology. We cannot afford, for example, failure of new technologies that we don't master totally. When we have a computer, when you have a personal computer, PC, if it fails, it's still, and then you have just to restart it, and then then we can work again. We cannot do Control-Alt delete in the grid. Actually, that's not possible. And now we have to accommodate actually some of the operation that need to be done in decentralized way, whereas we have a whole structure that is built in terms of centralized operation. The same thing from the economical, the question of who's going to pay, but beyond that, we need to find the right economical model or business model. Some of the solutions we have them, but still we are lacking some of the business model, and even for the viability of the solutions to be accepted actually by the end user. And of course, the regulation, because you have prior and post in regulation, we call them incentive versus a posteriori actual regulation. These actually the effect also the solution that we can imagine in the grid. So those are three general concepts, and I want to let you know that it's not only in terms of solution, but we have the concerns that are linked to the integration to the grid with respect to their constraint and economical viability and the regulation issue. So here's the picture, this smart grid evolution. It's actually worldwide. Okay, it's worldwide because the fundamentals actually of the drivers that I just indicated earlier are the same everywhere. What's different are the priorities. The priority, of course, for France may be different from the priority for the North Americans, and maybe, of course, and they are actually different from the priority for the Asian and for China, for example. But nevertheless, in terms of the value chain, in the value chain, where is actually the smart grid? Where is the smart grid? The whole value chain is affected in terms of in generation, in transmission, in distribution. They are affected. Although at the distribution level, it is mostly affected for the reason that I have explained earlier, because distribution grid was not designed for this evolution, because most of the generation renewable energies, as I told you, 95% are at the distribution level, because the architecture, I mean the topology of the distribution is not suitable for that, because of the electrical vehicle is at the distribution grid, because distribution grid is at the interface of the end user, and the end user now is becoming, of course, active and getting participating actually through some of the interaction with the grid. For example, the fact that now through a specific portal that can be, for example, meter or a smart meter, then the end user might propose actually some services to the market or to the grid, and those services can be on terms of course, demand response, for example, or flexibility, because it may be flexible, having in mind that the end user now is not only just a passive customer as it used to be, but the end user now can be a producer, because it can have some photovoltaic panels on his roof. It can have some storage. It can have the electric vehicle that can work both directions, etc., etc. So just have a look that traditionally, because we need to keep the balance all the time, the balance between generation and consumption. So the consumption is evolving traditionally all the time, and in order to keep that balance, actually, we act on the classical generation in order to keep that balance, because we are able to do it because these traditional generation are controllable. Now we can control them. Okay, but when you have the generation that is maybe not controllable because it depends mostly on weather conditions such as wind and PV, so maybe not controllable, and the consumption is varying. So for keeping this balance between generation and consumption, who's going to control who? And this is one of the key questions. Who's going to control who if we have only this kind of generation without obviously a large scale of storage, okay, because the storage may play a key role here. But what the change in the paradigm here is that we rely on some kind of flexibility that can be provided by the end user, so the end user can participate in this balance. And one of the prospect actually is that the end user may have to synchronize actually its consumption to the availability of the energy, and this is a big change in the electricity grid generally. Of course, this is a movement. It's not right now the situation, but it's going to. That's what we prospect actually in the future, and this situation where the end user can participate through its flexibility. So this can be more effective if it's done through the grid. Okay, through the grid, because the grid is a damper somehow. It's a damper, and it provides, and that the grid has the economic value because it provides the value for each user that is connected to the grid through its pooling effect. Okay, the pooling effect gives the value. So that's the grid that plays this role, but. Clearly, we still ask the question of the future of the grid, and we'll get back to that. In this chain, the smart meter, the smart meter is a key element of the smart grid. But you can see that it's not the only one because the whole chain actually is affected. So there are in order to test some of those solutions, there are a lot of business cases. I would not some use cases. Some use cases in order to test some of those solutions. I will not details on that. Some of the examples, of course, the safe and economic integration of renewable energy sources and new usages, for example, flexibility issues with the demand response, how to manage the fault quickly in order to increase the resilience of the grid, the new generation of the substation that may be safe and communicating, adaptive protection, and so on. So there are a lot of technologies that have been tested through a lot of demo projects. And in France, we have tested, actually, we have run through over 120 projects on the whole French territory, a project on smart grid, demo project, okay? Demo project, and those projects, they were dealing with the whole energy chain, generation, T&D, and customer involvement, from planning to operation, and grouping, extending stakeholders from academia, research center, industry, local communities, regulators, and so on. And what happened actually is that to prove this innovation and validate some of the technology options and open up future R&D directions, and of course, before that, going from demo project to deployment. You can see here the use cases here: electric vehicle integration, REST integration, storage, load management, and so on. And
Mr. Said, we have 5 minutes left, and there are a couple of questions. So if we want to have 5 minutes time to exchange.
I have just a couple of slides, and then we'll finish.
Okay, so 5 minutes. Thank you.
Okay, so and today actually we have just completed actually three large scale deployments. If we went through a demo to deployment, and deployment in 3 regions, and then from those deployment we can go further to the whole territory. This is just to let you know the France with respect to to EU, and this is interesting to see in the budget that are allocated, and you can see here that France is number 1 in Europe according to GRC, and you see that interestingly is that most of the funding comes from the private sectors, which means that they foresee some business in this area, and that's why they have this investment. And finally, what's next? The next is that definitely our energy system will be more electric. 2 times of the demand will be for electricity by the horizon 2040. It will be distributed. 70% of the generation units by 2040 will be renewable energy sources, and we still have to accomplish some more steps in terms of efficiency, and our energy system will be more connected. And the emerging consequence is that we are going towards maybe more DC. So this is the reverse of Edison somehow, because of renewable energy systems and efficiency, emergence of local actors, communities, and so on. I think that there are some projects in this area, and there is a change in the paradigms, economical and technical. The fact that we are going from marginal cost for the generation to service offer, because the marginal cost of renewable energy is zero for virtually. So we're going to service offer, from passive consumption to synchronizing the demand to energy availability, and from microgrid actually to blockchain and concept peer-to-peer energy. Definitely we're moving to more. We have to manage more local grids, local cells, with challenges related to the grid value. If we have only cells, what the grid value is? It just for the security at the end, or we still have to keep the pooling and the economical value of the grid? The market models, because more we go to local, the market is questioned, because from the theory to the economical theory is that the more is global, the more the most is fluid actually, and the quality of service, because the resilience is ultimately the key issue. So we have some issues related to distributed energy at local with this local management, where we embed some of the technologies there and interacting with local cells. With those local cells, we can find different kind of intelligent functions in terms of protection, in terms of flexibility, in terms of control, and so on. And one of the example, and I'll finish here, one of the example where we embed this distributed intelligence with the whole impact of the grid is a kind of the transmission. People, they know that the droop control that traditionally was on generating units, and we have put those droop control, translated it at the end user for flexibility issue, and then distributed largely on all the end users. And finally, we're able here to really to add a new margin for controlling the grid when it is faced to high variability. There was a test, for example, in one island here, where without this flexibility, we were facing a blackout. Whereas when we could put this distributed intelligence, then we can almost keep the system operating correctly. So since I don't have time, I will just immediately go to some messages. And this is my conclusion, and thank everyone will be happy. Well, one thing is that we're going from heritage to definitely innovation. And my message is that keep the system view, avoid the analysis by segment. Don't opposite local through global. They are complementary, okay? So local and global. And we're facing a remarkable field of technological development, and for the people, for example, SMEs with business development, actually. And the question here and how we can manage those transitions for more smarter grid. Thank you for your attention. I'm sorry if you have spent more minutes than what was initially allocated to me. Questions?
Thanks, Mr. Achtaid. It was a very rich presentation, very good and interesting. There is indeed one question in the chat. Would you recommend the generalization of electrical heating for the future? Could the national grid support such a change?
Well, the answer to this question is actually related to what's going on in the buildings. Because if the buildings they are energy efficient, if they are very energy efficient, which means that the leaks and the waste are so low, then yes, the electric heater is more effective. It's because its investment is very low, and if the building is efficient, electric vehicle is mostly most important. This is my view. Some of the others, they may have a different view, but there are some analyses that showed that yes, the electric vehicle, the heating, if the building is very efficient, or the house is very well isolated, insulated, then electric heater is more appropriate.
Okay. Also along.
Basically, that's what I do for my house.
Okay. Yes. And also along with well, let's say generalization of electric vehicles, it can both be supported.
Well, this is also a very good question, because we are facing this fast increase of penetration of electric vehicles. Well, there are a lot of studies done by different entities, by the transmission system operators with respect to the overall balance, by the distribution grid operators to see how he has to accommodate the electric vehicles. So there are a lot of studies. And basically what it states is that there will be the impact. There will be the impact for the distribution grid, for example, in terms of constraints, for example, voltage constraint, but also in terms of aging of the infrastructures at the transformer level, for example. There will be impacts. Okay, this is clearly. But if we introduce smart charging, as just indicated, smart charging, which means that we don't add the charging when it's a peak demand. We try to charge when it's at the valley. Well, I'm saying something very obvious because it has been very well documented. Then we will be able to accommodate the arrival and the generation of electric vehicle. We will be able to do that. Now, the question for which is one of the messages I insist, is that there is absolutely an important coordination. It needs to be coordinated when we develop actually the infrastructure for charging, whether it's for example, fast charging. It has to be coordinated with the operator, with the grid operator, because also we have to know that we may install, for example, charging station in, I would say, in terms of days or months, but in order to, for example, reinforce the grid, that it's in terms of years. So there is a mismatch So that's why we can do it, but provide we need to make it in a coordinated way between the installation of the charging station and the development of the grid. So it has been coordinated with the grid operator.
Okay, thank you. One last question, and then we move to the next one, because the next challenge will be the regulatory aspects as well. So between the original tree architecture and the completely distributed architecture, one participant says that the winning solutions are somewhere in between.
I perfectly agree. I perfectly agree, and this is one of my message, because I said that please don't consider, and this is for all the decision maker, don't consider the system by segment. It's one system, and don't opposite the local with the global. They have to work together. Sometimes it's more efficient when it's local. Sometimes it's more efficient when it's global. In terms of optimization, it's always more global is the more is optimum. But sometimes it's local. It's interesting. And in terms of architectures, it's not one against the other. It's not fully distributed against fully centralized. It's always some in between. When we see that it's more efficient that is distributed, then we distribute the intelligence. When it's more efficient, then we need to have some more coordination. Then it will be more global. So both of them need to work together. Definitely, I do agree.
Yeah, many thanks. Yeah, and we need to be smart everywhere.
Definitely.
So many thanks. Many thanks. So now I am happy to welcome our two new speakers that will talk about regulatory aspects in smart grids. So I'm happy to welcome Guillaume Magnin and Guillaume Bullier, Guillaume duo for this presentation. The floor is yours, gentlemen.
Hello, everyone. Can you hear me?
Yes, that's perfect.
Hi.
Okay. So we have a presentation divided in 3 main steps. First, we'll introduce the smart grids and the French energy context. And actually, some of the topics we will introduce will be a bit similar to what have been said before, so I might go a bit quick on this part. Then we will present to you some of the way CRE is tracking innovation and driving the reflection on future developments. And lastly, how we try to set up the right regulatory framework and some of the tools we use to do it. So as it has been said, one of the first main aspects of the smart grids is that today networks are gradually digitized. So smart meters are currently being installed in all of the networks, and it will enable a reduction of costs, non-typical power losses costs or metering costs. So far, there are around 30 million smart meters that have already been installed in the distribution network, and it will be about 35 million by 2021. The data these smart measures provide are already been can already be accessed by authorized third parties through different channels that have been implemented by the TSO/DSO. And actually, the challenge for the regulator today is to ensure a balanced framework to facilitate data access. So actually, the third parties, including the energy supplier, can propose new services to the consumer, while at the same time, we want to ensure that the data of these clients are effectively protected. As it has been said by the previous speaker, the public grid is now being used in so many ways. So, for example, renewable energy sources are developed everywhere in all parts of the network. There is also electricity storage that is increasing. Self-consumption and energy communities, electric vehicles. And actually all these new users need to have a non-discriminatory access to the network and to the system. And this is the second main challenge that actually CRE is facing. And we have been conducting some works on each of these use, and actually this will be detailed in the presentation. Last but not least, as you know, RES are intermittent, and as more RES producers are connected to the network, more flexibility is needed at the system level. And actually, this flexibility assets may come from different sources, such as controllable charges, so production, storage capacities, or sector coupling. And actually here, the challenge for the regulator is to create a legal and regulatory framework that enable third parties to offer flexibility services to the grid operators, and therefore limit network reinforcement to what is strictly necessary. And actually, there are some works as well here that are being done as from the regulator, by the regulator, and actually also by the TSO/DSO that are launching some calls for tenders to enable third parties to present and to propose their services. And if we go next, here we are going to introduce to you, as said before, how CRE is tracking innovation. So first, and historically, it has been one of the first things CRE has done. CRE identifies and closely follows smart grids project in France, as well as some projects in Europe. But today I will be more focusing on the projects which have been done in France. So CRE sits on advisory boards of some projects and is in regular contacts with project holders to help projects roll out. So actually, if you are leading at the moment some projects that are currently not being followed by CRE, do not hesitate to enter in contact with us to so we can work together and follow your project. And CRE publishes reports on smart grid demonstrators, in which CRE identifies solutions that will help the system to be more cost-effective or more efficient, and should be developed. And in the other way around, solutions that did not meet the expectations and shouldn't be industrialized. The last report we published in June 2020 focused on 15 demonstrators. And these 15 demonstrators focused on solutions aiming at integrating the new uses of the network, optimizing network management, and proposing energy database solutions. And yeah, so if you want to get more info, you can go on the website of CRE, and this will be accessible. And here are the main message that actually we had based on our analysis. CRE asks, in fact, the DSO develop all solutions to increase network capacity for the integration of the renewable energy sources. It comes from smart grid connections to the curtailment of some production. CRE has asked also the network operators to develop or introduce a technical and contractual framework to enable temporary consumption curtailment of voluntary users to provide flexibility services to the DSO. So in fact, this solution has been trialed to avoid the blackout. So actually, when the DSO sees a blackout coming, it can lower the consumption or the power consumption of some users, the voluntary users, to avoid the blackout. And actually, we wanted these solutions to be developed. CRE has asked as well the DSO and the TSO to give access to authorized third parties to data and functionality of the smart mirrors. Actually, smart mirrors and most of the functionality of the smart mirrors have been thought to be the excess of these functionalities have been done for the energy suppliers at the beginning, but actually some of these functionalities can help the authorized third parties to provide new services. So actually, this is why we wanted to give the access to authorized third parties. And last but not least, CRE has asked also the DSO-TSO to continue their collaborations with stakeholders in favor of the industrialization of the smart grid solutions. And actually, this by this we also mean providing CRE with feedbacks of the demonstrators, so we can have a more info on what solutions need to be developed or not. And now I will give the floor to my colleague, Guillaume Bullier.
Thank you, Guillaume. Within its responsibilities, CRE also has to animate a debate among the ecosystem about the future of our energy grids. To this end, we manage a website on smart grids, which provides free and unbiased information about smart grids in general and also technologies, and also about projects held in France. It's a website open to contributions, and we have several external actors that contribute to the website. When we do not have pandemics, we also hold events like workshops and forums to generate a debate and communicate about major issues on smart grids. CRE also closely works, closely studies the work of the networks operators, and we publish reports on smart grids to formulate some recommendations and specific demands for the rollout of smart grids in France. More recently, we focused first on electric vehicles. We formulated recommendations about smart charging and the optimization of the connection and of the location of electric vehicle charging infrastructures. About storage, we formulated recommendations about the simplifications of the market access rules and the connection rules of storage to facilitate their participation to the flexibility mechanisms. We also ask the network operators to take flexibility solutions into account for the network design and to communicate transparently about the local needs for flexibility in order to so that some actors can provide flexibility where it's needed. We also have to set the right regulatory framework to allow the development of smart grids in France. And the energy and climate law introduced in France the regulatory sandbox, which allows the minister or CRE to grant temporary exemptions to some project holders, temporary exemptions to the network access rules or the network usage rules in order to experiment innovative services and technologies aligned with the energy transition goals. During the last window, we received 41 demands from various project holders. We are going to publish a decision very soon, and some of the project holders will be able to lead the experimentations related to very important subjects on smart grids like power to gas, storage, and local flexibility. We will open a new call for project during the year, probably at the second semester. Finally, CRE's responsibility is also to give to the networks operators the resources and the incentives to carry out their research and development. So it was taken into account in the definition of the expand trajectories of the operators. And we introduced a smart grid counter, which enables the operators to ask for additional funding for smart grid investments. To finish, to create incentives for the network operators to take specific actions which are necessary for the development of smart grids and for the development of innovations by external actors. We created a penalty mechanisms in case of delays in the implementation of these necessary actions. These actions must lead to concrete results in the research and development programs of the network operators and the effective use of flexibility sources and all innovative solutions that can provide services to the network. If you have some questions, we still have a few minutes to answer. And otherwise, I recommend you to don't hesitate to contact us at the email address that were displayed.
Many thanks. Yeah, indeed, we have a couple of questions for you too. Is active power curtailment of distribution connected RES from DSOs allowed? Like it's written also operation set point control from DSOs.
So to be honest, I don't know the whole regulatory aspects, but actually I know that in some contexts the curtailment is possible. So, for instance, in the case which is really specific of the smart grid connection, actually the DSO proposes to the producers a connection, a connection to the grid, which do not enable the full production at all time, but actually the connection is a bit cheaper. The delay is a bit to build the connection is a bit lower as well. So it's more efficient connection. and in exchange, the producers have to be curtailed in some part of the year, which are quite not quite often. And so in this case, curtailment is possible. I don't know if I answered the question well.
I hope so. If Georges wants to react on the chat, if this is yes, thank you. Do you cooperate with energy, I guess, industry associations, the syndicats in French, and their local representations?
We are in relation with them about local projects and the network, the local distribution networks. Of course, to study with them the innovative projects that are led on the territories, and we are at the disposal of all local actors to answer their questions and understand their needs about the future of the regulation.
Okay, thank you. Well, a bit more largely, but how about safety regulations? Do you operate on that? Is it one of your duty, or? I guess the safety of the grid, yeah. If Luca can maybe precise.
That's not an exclusive competence of CRE, but the safety is part of some aspects that are studied, for example, in the regulatory sandbox for the power to gas and synthetic methane injection in the grids. We have to study regulatory safety aspects before allowing some project and some derogation to the regulation, and to allow to generalize those derogation to allow some innovations to happen, which may have some safety consequences. So it's really studied with the collaboration of the minister and the network operators, of course.
Okay, thank you. Okay. How do you take into account local public authorities who are the real owners of the distribution networks when you are proposing recommendations? So by public authorities, it's meant regions and departments, French regions.
So there are many ways. The two first that come to my mind are actually we quite regularly proposed public consultations in which all the stakeholders, including the local public authorities, are able to discuss some of the recommendations we want to make. So this is one of the first main part. And actually, on the second hand, for instance, in the regulatory sandbox, we are obliged to come to the local public authorities when it comes to some specific aspects of their competencies. And this enables us to be in close contact with them to make sure that our recommendations are aligned with actually what their specificities are, I would say.
Okay, maybe a last question, because we are a bit behind of schedule. If you have time after to discuss this in the B2B meetings, that would be great. So can you please elaborate a little bit more on what is understood under the CRE regulatory for smart grids in Africa?
Sure.
This is a question for one of our Flemish colleagues, apparently.
Yeah.
You want to go back to the slide or on this or no?
No, I'm sorry. I'm not able to elaborate a bit more. I don't have all the history on smart grids in Africa and the regulation. But I may answer the next question. Do we take into account the environmental aspects? Of course. Of course, the goal is to regulate the networks in order to facilitate the energy transition and to answer the climate issues. But of course, we tend to be as neutral as possible about the different technologies that may answer those issues. And we try to set the best regulatory framework that will allow all the potential and all the best technologies to be developed and to answer the environmental issues.
Okay, many thanks. Many thanks to both of you. If you want, maybe you can leave in the chat your email address if you wish, and so that you can further exchange with the participants. We are here today over 40, coming from mainly Belgium, France, Switzerland. So yeah, and then Poland as well, and other countries that I might forget. Sorry. Okay, thank you. So I'm inviting now our next speaker, Michel Benat from RTE. He will talk about smart grids as solutions to optimize the electrical system in real time. So,
okay, do you hear
Benat, me? Yeah, we hear you. Thank you. So,
fine.
Yeah, just you have a couple of slides. Just we are 5 minutes behind schedule, but it's still okay.
Okay, I try to be fast. So thank you for your invitation. So my name is Michel Benat, and I'm a Deputy Director of the Research and Development Department of RTE, the French TSO, a department that is located in Paris. Through my presentation, I want to show the specific role of RTE as a transmission operator. That is, it is a place where to mutualize and optimize all the flexibilities in real time. And the second point is that as we have to take decisions today for the future, what are the concrete decisions we take in RTE to prepare a smart electric system for the years to come. So a few words about my company. Okay, so it's the first one. For those of you who don't know RTE, a couple of key figures. So RTE, the only owner and operator of the transmission grid in France, and that goes in France from the 400 kV down to the 63 kVs, and we have distributing company that do the job for the other voltage levels. So we have around 100,000 kilometers of lines, and 1/4 of them 400 kV, 2,000 substations. An important thing, we have 46 interconnections with other European countries. That is Spain, Italy, Switzerland, Germany, Belgium, and England. And we are about 8,000 employees with an income of 4 billion euros. Noureddin Al-Said spoke about the local and global. Here is an example of the global trend at the European level, since we intend to develop new interconnections. Here you have what we call 4 packs. The first one, pack 0, with a couple of interconnection, means that some connections are already under development. Even some of them are already commissioned, such as the IFA number 2 between France and England. Then we plan to have a pack 1 that is new interconnection that we will build with no regret. You can see there's an additional connection between France and Spain through the ocean, and a new interconnection with Belgium and with Germany. And then we have all the packs of possible new connections that have to be more studied, because the criteria or the incentives are not so clear today, and we have to do more studies to be sure that this new connection worth it. The important thing is that the power exchange capacities between France and the other countries will be doubled by 2035, and that means that it will be a new level, a new way, to a new flexibility to optimize the European system globally. For a French TSO, or for TSO in general, we have two main missions. The first one, of course, is to keep the generation load balance in real time. The TSO is the only stakeholder to have all the information in real time to keep the system balance. And the other thing is that we have to optimize. I put it in quotes on brackets, because the optimization functions maybe will evolve in the future. Today we have to take all the most economical solutions in real time to ensure that we go from an unbalanced system to a balanced system. But maybe in the future we will have all the criteria such as environmental issues or others. So it's an important thing to keep in mind that the TSO has to keep the generational balance in real time with an optimization function that may evolve in the future. The other thing, another, of course, important mission is to decide today what will be the grid in 5 or 10 years. You know that it takes a couple of years to have a new line of a new infrastructure on our grid. We usually in France, we say that it takes around 7 years between the decision of a new line and its commissioning. So when we have to think about what will be the grid in 10 years, we have to take into account the fact that we have to optimize the smart development of new infrastructures, but including future available flexibilities. We have to take into account the fact that in 5 or 7 or 10 years, we have existing flexibilities or maybe new flexibilities that can help the system to work properly at the lowest cost. So the purpose is to minimize the cost of the development of the grid, taking into account these flexibilities. And that's a real challenge for us. And I give you an example of what we decided in our last study for the 10 years to come. The thing is that when we speak about smart grids, we speak about flexibilities. The definition of flexibility is that flexibility can be understood as the system ability to adapt to variations. Of course, the most popular flexibilities are the ones that are activated in real time. But to be sure to have the good flexibilities in real time, we have to prepare it in a different time horizon. On the top of the slide, you can see that we can prepare new flexibilities 5 years in advance, 1 year in advance, 1 week in advance, a day ahead, to be sure that in real time things will go well. And all these flexibilities have to be able to adapt to either the predictable variations that you can see in pink on the top of the slide, or the unpredictable variations. And you can see the variations are not the same if you take the situation 1 year in advance, 1 week in advance, or in real time. As to the possible flexibilities to be activated, you have the conception, the generation, the grid. Of course, we can have flexibilities on our infrastructures or in the way we operate it, or maybe in the future you will have more and more storage devices. And if you see the line grid, you can see that 5 years in advance, we already have to take decisions, and I give you examples, on investments. Our investments must take into account the fact that in 10 years, in real time, we can use flexibilities that are prepared today 1 year in advance, we use a maintenance procedure to adapt the way we operate the grid. Day ahead, we can play on grid topology, and in France, we like to play on grid topology, and that is not the case. That is not the case in other countries, such as Germany or others. And in real time, we can play on grid settings. So first, I will focus first very rapidly on the real-time flexibilities, because as I put it, they are the most popular, and maybe the Graal or the paradise could be to react instantly with all these devices. I think that will be never the case, because we take time to operate the system, and maybe we can have all the automatic reaction of all the stakeholders in real time. But of course, the purpose is to be able to take into account all these devices. In the middle, you see the French electric system, so the role of the TSO. And in real time, RTE can activate, if needed, flexibilities in real time. And this flexibility can come from the renewables. You can see it on the top on the left. But to be able to reduce, to curtail, or to use the ancillary services that can be brought by this new generation means, it has to be prepared. So we needed all the European grid codes that are elaborated by all European TSOs to be prepared in real time, to be sure that we can rely on the renewable to take part to the system resiliency. We can, of course, rely on consumption, on demand response. You can see it on the right. Today, I think France has one of the most relevant market design to promote demand response. Today, we use mostly industrial demand response to help to keep the frequency, at least in France, but also in Europe. And I think you know that in a couple of weeks ago, we had a problem in Europe, and we had to act very fast on demand response through some big industry in France to keep the frequency at the relevant level. Of course, we can play on the European flexibility, taking advantage of the interconnection that I mentioned previously. And we can play. It's not the case today, but I guess in a couple of years, we will have the possibility to play with storage devices such as batteries or big batteries, or the batteries that are in the electric vehicles. And you can see an arrow that goes from France to France. That means that we also can play on our own infrastructure in RTE. So the other thing that I wanted to put forward is that what we take in terms of decision today, how we integrate the future flexibility in our decision on investment today. So we are in the line grid with the flexibilities 5 years in advance. Is what it was mentioned by Guillaume Magna, I guess, that today the purpose is not to spend too much money on the grid. We have to take into account the fact that we have digital solutions that can optimize the existing and future physical infrastructures. On the left, we have the observation is that if we size the grid to evacuate 100% of the renewable installed power capacity, it will cost too much. Since wind park or PV produce at their maximum only 10, 50, 100 hours, a year, and we cannot size the grid only for these 100 hours. So to build new infrastructure that would only be needed a few hours a year is not relevant. It's unnecessary investment for the community. So the choice that we took today is that we have to mix a partial grid reinforcement. Of course, we will always need copper, new infrastructure, but we have to combine this grid reinforcement with production curtailment and other flexibility activations, such as monitoring and storage. And we have what we call the optimal grid sizing, that is less costly than the 100% grid sizing.
5 minutes left, Mr. Bena.
So we use what we plan to develop and to deploy in the years to come is that what we call automata. NASA in French stands for New Adaptive Automata for zonal issues. So we will have automata, one automata for 1 to 20 substations. These automata will take into account the power flows in input, the max flow capacity on the lines, the grid topology, the outage detection, and will take automatic decisions to have actions on grid topology, to curtail the renewable productions, or to decide other flexibilities activation. If you, for example, if I have an example on the max flow capacity, we deploy dynamic analytic devices, and you know that these devices can take into account the temperature, the wind power, and what is the impact of the wind on the temperature of the cables. And if you have a strong wind, of course, you can have a lower temperature in the cables, and you can have more megawatts going through the cables. So we plan to have more and more monitoring system devices such as this on our lines to be able to optimize in real time, to compute in real time the capacities of the line and to take advantage of the capacity in real time. Of course, as a result, we will have to curtail some of the production. What we computed and presented publicly 2 years ago is that if we curtail only 0.3% of the renewable energy by 2035, we can have some significant grid saving, around 7 billion euros by 2035. Initially, we plan to have around a budget of 45 billion euros of grid reinforcement by 2035. With this slight curtailment, we can save already 7 billion euros. So it is very important. Another thing is that we can activate other flexibilities. So we have a Ringo project. The Ringo project is a large experiment with 10 megawatts batteries that are located in 3 substations in France. Of course, it's not economically relevant today, but the first thing we want to see is that how it works in real life. What are the benefits that can provide storage connected to the substation with multi-services in the future and so on, and to be sure that we can use it in the future as a flexible devices, operational and economically relevant device. So it's an experiment that only begins, and we hope to have results in 2 years. And we use also smart wires. Smart wires are devices that are put in the lines and then can modify slightly by a couple of % the impedance on the line, so it can change the flows on the line while keeping the same infrastructure. And my last slide and my last minute, I guess. And of course, all these decisions, this proposition were made in what we call the French 10-year development plan. It's a document that says what we plan to do in the 10 years to come. We presented this document in September 2019, and it was approved by the French regulator last year. And what you can see is that if you see the figures or what I put on the bottom of the slide, is that at the beginning we plan to have 45 billion euros in investment, and at the end, using all these flexibilities, we can have 10 billion euros saved money. So it's really important. And the purpose is also to be sure that the transmission cost is stable and that it always represent only 7 to 8% of the final consumer bill. And we have I think a couple of figures comparing different countries. To be honest, I don't take the time to know where it comes from, but it is in our report, and it says that when you see what are the plan invested billion euros per new terawatt of generation energy, considering of course the past, the fact that France has a strong grid and so on, France is quite in quite good. It's quite the good how to say it, a good figure. And you can see that it will cost much more in Germany or in Great Britain, and that France is much closer to Italy or Spain. And we think that we managed to optimize investment for the 10 years to come and be able to accompany what you already mentioned at the beginning is a huge objectives that are wanted by the French government considering the renewables. That was my last slide.
Thank you very much, Mr. Bena. A few questions. How do you manage people opposition to building new power lines?
We don't have we are in the process to we have of course a specific department to work on this topic. We don't have the solutions today. There's no final solutions. When you decide to of course when we decide to build a new line, it has to answer to a need in terms of renewables or mostly the renewables today. In the past, the purpose was to be able to get enough energy for the consumption growth. Today, the consumption is quite flat, so the main driver for the new lines are renewables. And there's a large opposition not only for the lines but also for the renewables. There's a large opposition for the new wind plan, mostly in France today, and we try to work with coordination with politics to explain what are the purpose of the plan. But we don't have the solution today to this topic. What I can say is that when I mentioned that we need 7 years to build a new line, it takes 5 years to speak with people and 2 years to build the infrastructure.
Okay. Good. Why do you consider weather as unpredictable variation, especially if you are in real-time operation? It was a reaction to one of your charts.
Yes, in real time you can have suddenly a strong wind in part of France, with suddenly large power coming in part of France, and you cannot predict everything at that time. And suddenly you have a wind park that will come to 100% of that generation, and we need to react to this with things. So it's more locally weather unpredictable variations. At the French level, in real time, we don't have such events because of the mitigation of the wind effects and the solar effects. We can predict quite well what is in real time the overall wind power or PV power, but locally, and it was mentioned by some other people, and I guess that Enedis will see it after that. We try to more and more have local operation with local constraints and react locally. That's what I mentioned with local automata. This local automata will have to react to weather in real time. And if there is a strong wind with 100% of the wind park generating energy, we'll have to react with automata in real time, locally.
Okay, thank you.
And if we have a fiber optics,
yes, exactly, optics along your cables.
Yes, we have about 25,000 kilometers of fiber optics out of 100,000 kilometers of lines. We use it for our needs to operate the grids, and we also propose services to the operator of internet, or if we have, if we can. So we plan to use it either for our own needs or for the internet operators. They can use it for their own needs.
Mm-hmm. A last technical question. Do you consider voltage control multi-objective optimization with artificial intelligence due to your large number of control assets?
Of course, we have a lot of devices to control the voltage control, but we try in our R&D department to put artificial intelligence in the reactive control, but it's not yet conclusive today. It's not yet conclusive today. We try to, you know, when you work, technically speaking, when you work on artificial intelligence, there's a first phase of learning. Try to learn to learn the past, to understand the past, to see what are the key drivers. And today it's not very easy to understand, to learn what can be put in the artificial intelligence basis to take automatically decisions. But it's an R&D topic today. It's an R&D topic, but we are not yet ready to put automatic decision on reactive and voltage control today.
Mm-hmm. Okay, thank you. And last question, or more an assumption, I don't know, from Mr. Said, but then I would just leave it as an open idea, and we move to the next one. But can we say that thanks to RTE real-time control capabilities, including demand response available options, we say that France is the frequency safeguard for all Europe?
Yes, I tried to put it, but a couple of weeks ago, you know, there was a lot of people saying that we were close to the blackout in Europe because there was a contingency in the east of Europe. Then the frequency dropped, and the frequency is common to all of the countries in Europe. So we saw the frequency drop also in France, and we took measures in France through demand response, and we automatically ask big industry to get out of the system and to keep the frequency in the good range. And yes, it was a good occasion to promote the French mechanism of demand response, and to see that automatically and very fastly, because you have to react very fast. We could with mechanism put back the frequency and the European frequency in the good range. So it was a good example of the mechanism that we put into place in France for the benefit of all Europe.
Good conclusion. Many thanks, Mr. Bena, and to all participants as well for the good discussions. Let's move now to the view of national distribution network operator, and I'm glad to welcome today Jean-Philippe Poirier from Tenerrdis, and he will present, his presentation is called leveraging a more digital network.
Well, thank you, Laure. Hi, everybody. I'm truly pleased to join in this panel. My name is Jean-Philippe Poirier. I run the industrialization of smart grid solutions at Tenerrdis, along with the smart grid program. Today, I'll be able to share with you and give you a first glance at the development, the deployment of a more digital network, leading to an increased observability at all levels of the distribution network. And you'll see that it allows us to interact in a more targeted, quicker, more efficient manner in the field. We'll talk about Linkygrid project. You'll see we use the metering infrastructure and make the best out of it. you'll see also some example of connected devices, referred to IoTs. And in a second move, I'll talk about all the efforts that we're doing with big data and artificial intelligence in order to build new analytics, new analysis capabilities and anticipation capabilities. So I'll suggest that we get started with just a first glance at I believe you might see it, the key figures for Enedis. So Enedis is a distribution system operator. We heard the name Enedis in the presentations that were done by Cray and RT. We are the main distribution system operator in France. We operate 95% of the grid. So I won't delve into the numbers, the figures. You see them. You'll probably get the slide as well later on. What I'll suggest is that we focus a second on this slide. As you can see, at Enedis, we're implementing a massive digitalization of the distribution grid itself. You can see on the slide the different kind of equipments that are installed. Some are really new equipment, some are just upgrades of previous kinds of equipment. You'll see that we are deploying sensors as well and actuators from all across the value chain of the distribution grid. So starting on the left from the digital primary substations, the link between the TSO and the DSO, up to on the right, the Linky smart metering infrastructure. So at the end user level, you'll see also that we're able to collect a lot of data, and we're trying to make the best out of this data and leading some work on the AI and big data field to have a better and more efficient network. I probably would like to suggest that we share a short animated movie. I think if it works, maybe I need some help from Laure to launch the video.
It works.
Within the framework of the Linky program, Enedis is installing 35 million meters and 700,000 concentrators, which are so many new sensors on the distribution network. Beyond measuring consumption, Linky provides additional features to improve network management. The Linky infrastructure records and transmits data relative to the operating condition of the distribution network. LinkyGrid enables cross-referencing between the Linky information system and the network management information systems. It provides innovative functions to help network management operators with their task. LinkyGrid enables the setting up of a comprehensive supervision of the low-voltage network. In the case of an equipment fault or wire breaks in conductors, operators are notified in real time. Detecting and localizing a fault, even before the client calls in, becomes possible. We save time. Several features are already available. Among these, since 2015, call center operators can ping the Linky meters to diagnose the type of breakdown when the customer calls in. Since 2017, grid supervisors can improve their analysis by remotely interrogating targeted Linky equipment. Beyond real time, LinkyGrid helps cartographers reinforce the geographical information system accuracy, especially by associating customers' meters with their secondary substation and even with their low-voltage phase. LinkyGrid is, lastly, an improvement in the monitoring of power quality thanks to a better knowledge of outages and voltage excursions experienced by customers. When they are compared to information from the network, these contextualized data help to address customer complaints more efficiently. Beyond that, when abnormal network situations are detected, these are subject to closer and automated observation. Using the data collected as a starting point, algorithms can suggest simple field actions, which then enables investments to be better targeted. With LinkyGrid, Enedis's reactivity is strengthened for the greater satisfaction of its customers.
I guess we are now on your slide on Linky Grid.
Thank you.
Thanks for this video.
Yeah, very good. Well, so as you were able to see and witness it, the Linky metering infrastructure is just a bit more than just a meter and information systems with it. It helps us to enable low voltage network supervision, which is a very a new feature. We were able to have features like this on the medium voltage side. It's been years with that, but on the low voltage we were blind. So it's very helpful to be able to act in the field in case of a fault, even before customers call. So it's changed quite a bit the way we operate the business, and we are able to be proactive as opposed to be just reactive when customers call and tell us that they are out of power. I'll move over to a different set of a different field. In the same way that we were able to move from a meter infrastructure that was working fine for years, and we made them connected. So it happens the same way with connected devices, so IoTs if you wish. We started with equipments that were already installed on the network, so it would be the low voltage or the medium voltage network, and made them connected. You can see on this slide 6 major solutions that were industrialized. Let's start with the backup generator. Backup generator, it's super useful when it comes to field work, when you need to cut the power on some ends and feed the customer with power that is not coming from the grid, but with backup generators. But it is also very famous for helping with crisis management when you've got a weather crisis. And backup generators, we made them connected with the help of manufacturers. We were able to get new features with backup generators, so such as the GPS position. Imagine that you are able to know the exact position, the exact location of a backup generator. In crisis management, you've got hundreds of backup generators that are in the field. Knowing where they are precisely, it helps to coordinate the efforts. Also very helpful, we're able to get a good feel for the operating status. We know if they're running or not, in a live condition. And we're also able to be notified with alerts of the need to refuel, because it's just such a pity when you've got a backup generator that runs out of fuel and doesn't generate power. So you need to keep an eye on this, and we're able to better coordinate all the efforts in crisis management thanks to that. So it's a real game changer. I'll move along with the other examples. I'll suggest that we move over to the medium voltage network management IoTs. I believe you're familiar with surge arresters. Surge arresters, some were connected, some are not connected. We were able to make them connected, so we have a better notification and alarms to help the location of faults. And it's the same way that we use fault detectors. And you'll notice that fault detectors on the medium voltage grid are very helpful to to quickly respond to fault on the grid. Also, another example, and I think that is also of interest, on the upper side of the distribution system value chain, it's the primary substation. We obviously have transformers, and these are critical assets. We are able to equip and retrofit transformers with an equipment that helps us monitor the health of these transformers. So there's no doubt that this is very helpful because it is used in an objective of predictive maintenance, and that helps us interact and intervene in the field at the risk of a failure of a transformer. Other example, and I think that is also of interest, is clearly crisis management. I already talked about backup generators, so we won't come back to that. This is helpful, I've said it. But also we also retrofitted secondary substations with flood detectors. It's very simple. It's how do you measure the level of water in the building? You get notified. You can better coordinate the efforts in order to cut the power remotely if need be. When the flood is going away and the water level comes down, you're notified of the fact that it came down, so you are able to be much more efficient with your field teams and go back, dry it out, and make sure that you can turn the power back on. So these are tools, IoTs, that are really helpful for us in crisis management times. And as you were able to witness, I believe we're one of the pioneers, and this is one of the pioneers in this field. We started with manufacturers, and they helped us retrofit existing equipment. Then we moved along with having native equipment, so they are natively communicating. So that is a very encouraging move from the manufacturers. And as a matter of fact, there is a new mode of interaction with manufacturers, because they now are coming with in front of us with already natively communicating devices, and that's the perfect examples for the connected cable reels. For the cable reels, it is the newest IoT, and there is obviously the possibility of GPS location, very useful. And also, and that's a key factor, the cable length that is left on the reel. So knowing exactly what is the status of your cable reel is truly helpful. I cannot mention that without going further with the AI and big data developments that we have at Tenerrdis. And I suggest that we move along with the following slide there. Okay, so as you may know, we collect data. We have data that is already in the expert systems, the information systems. So we already have a role into analyzing the data that is there. We collect the data, obviously, from the IoTs and all the equipments that I mentioned before. And we're also able to cross-reference this data and this new data. Along with new methods of new predictive models that are better able to help us to predict what's going to happen, obviously, and also cross-referencing data with image recognition. We have tons of pictures, photographs of equipment, and we are able to be much more efficient, and it is growing in terms of efficiency for knowing what happens on the grid. I'll give you probably 3 examples. The first one is on the left. We're talking about optimized underground cable renewal. So we're talking about field work. We're talking about designing a program to make the best out of investment money, and targeting where the cables need to be replaced as a priority. And we're able to do that by cross-referencing data that we have, statistical data on incidence location, geographic information system that we have, and pinpoint the areas that need replacement in first. So that is truly helpful. We're able to do quite some savings on this. We're doing that on low voltage. We're starting to do that also on medium voltage. Second example is obviously an extension of what we've done before with Linky. I mentioned earlier about Linky, and Linky helps us as well to collect data, and we were able to do some machine learning on the information that was shared, and we're able to predict. So it's low voltage predictive maintenance. We're able to predict at some locations where there is a high probability of incident upcoming. So that helps us. It doesn't work for all cases, obviously. It's still in the progress, but that is a true breakthrough in the way we operate the grid. We're able to, I mentioned earlier, we're able to go on in the field even before customers warn us that there's something going on. But also, as well, there's a good feature that helps us predict way ahead of time what could happen on the grid and the specific location. And the final example, it's just the fact that thanks to image recognition, we've been doing that for years. We take pictures of the overhead line, mostly on the medium voltage side, and we're doing diagnostics, but human diagnostics for programmed renovations. So to be specific, these are programs that aim at renewing some sections of the medium voltage overhead line, and we're able to perform very accurate diagnostics on the equipment that is present, and that helps us be more efficient. That helps us to be more efficient with money as well. So that's truly helpful, and we're able to do that with any kind of picture that is taken from a helicopter, but also the drones as well. So it's a very useful and common way for us to perform this kind of diagnostics. Well, I had a short amount of time today to probably give you an overview of these different techniques and different features, different equipment that we're putting on the grid. I'll be able to take some questions later on. So I'll thank you for your attention, and I'll be taking some questions if you wish. Thank you.
Thank you. Thank you very much, Jean-Philippe. Maybe first question from my side. Very impressive developments. Do you undergo them all internally, or do you collaborate with external partners? You mentioned the programs.
Obviously, there's the mix. There's a mix. So usually it's a matter of I would say industrial policy. Whether you make or buy some solutions, we design them in-house. When we talk about artificial intelligence and big data, we have data scientists that help us and work with us, and they are employees of Tenerrdis that help us design some approaches. For instance, the work that we do on the optimized underground cable renewal, that's a purely in-house project. Mm-hmm. But we also mix. And in terms of diagnostics for programmed renovations, image recognition, there was a mix. We tried with in-house people. We noticed that some outside people, companies were in the business of doing that their business. So we relied on the fact that they were at an industrial level, very already ready with the right algorithms, the right approach, the right human interfaces, portals on the web, and so on. So it was faster for a shorter time to market. It was easier to go with partners than build this ourselves.
Okay, good. Thank you. From the participants now, do you also measure energy flows per cable in the LV substations?
Well, I'm not in this business. We are monitoring flows as well, but well, it's clearly not the aim of the smart grid solutions that we're deploying.
Okay. Do you know the average cost for transformer health monitoring sensor devices?
Well, there's, I guess, it depends where you buy them. It depends where, because there are several kinds. The ones that we have, you need to account for something like 10 grand, so 10,000 euros. It's a minimum, but it has also to be compared to the cost of the transformer itself, and that is quite expensive. So it's 10 grand plus the equipment that and the workforce that needs to be put in place. But that's an order of magnitude.
Mm-hmm. Okay, many thanks. This is it. Thank you, Jean-Philippe. The video was a good success also. So yeah, we shared the public YouTube link to have it.
Very good.
And if all speakers agree, but I guess this is the case, we will share definitely the slides. Just be patient, maybe later on when all the webinar series will be over. Okay, thank you. Now I'm happy to welcome our last speaker for this morning, Youssef Shaibi from the company Green-Alp, and he will share with us his view from a local energy company. Good morning. Hello, Youssef. Can you hear us? Okay, we hear you. Very good. The floor is yours.
Yes, perfectly. Good morning, everyone. Thank you. Good morning, everyone, and thanks to all the speakers for this deeper and deeper dive into smart grids. And I'll go a bit deeper again with the view of a local energy company. So first, who are we? Why am I talking about a local energy company? Green-Alp, we are a DSO, a local DSO. In French, it's called une entreprise locale de distribution. And to understand that, we have to go back a bit to the birth of the company and how the evolution was those 150 years ago. So we started as a gas distribution company. Then power came 50 years later, in the beginning of the 20th century. And after the war, after the Second World War, in France, there was a big nationalization program that created EDF GDF. But at that time, the city of Grenoble kept the Régie Gaz and Électricité as a public company. So at that time, you had EDF GDF as a big utility in France, and several local units staying in some small cities and some bigger cities too. Then, since the Second World War until a few years now, we have some consolidation. So some of those companies have been merged with others. But still today, we still have this into the panorama. You just said before on the Enedis presentation that Enedis was the DSO for 95% of the country, and so those local energy distribution companies, those OLD, account for the 5 remaining percent of the national territory and the population. So who are we? We have power. And we have also gas distribution. We have 120,000 customers in power. So we are the 6th DSO in size, 45,000 customers in gas, and so the 4th DSO in size, both natural gas and propane. So in my presentation, I speak more about electricity, but then I'll open up a bit also with some natural gas, because we have there are some questions there also when we're talking about smarts, with the complementarity between electricity and gas. As you saw the map, I should have added a map of France globally to see that we have we're really small geographic area. You have Grenoble, that is the main city. In the middle, it's so the map is Isère, so it's one of the departments in France, one of the 90 departments in France. And as you see, we are operating networks on cities or on districts that are not completely linked, and that's something interesting, because Michel said on the RTA presentation that we have to consider the interconnection with the other countries, and for us as a DSO, we also have a lot of interconnection, not with countries, but not with other networks. Should that be the other DSOs, Enedis and the GRDF in gas, or the TSOs, so RTE and GR gas. So you see, to go from one scheme that we don't have is that to go from one part of our network to the other part of our network, we have no go through. I mean, we cannot go from Green Alp network to someone else's network, then back again to Green Alp network. So we have also only a direct. And same for the organization in Grenoble. RTE asked us to have a go-through Grenoble, meaning the power supply we get from RTE in one part of Grenoble cannot be given back to RTE from another side of Grenoble. So we have to consider Grenoble as a dead end, a consumer end only from the grid perspective. One specificity we have is that we are a société d'économie mixte. What does that mean? It means that the city of Grenoble and the metropolitan area, both of them are our main stakeholders. We have 50% stakeholders apart for the two of them, and then we have some major industrial partners as Engie or also EDF and Schneider Electric, for instance. Why do I emphasize on that as being something important? It is because it's part of our DNA and it's part of our will and connection to the local community. Grenoble and the surroundings is a territory when we have a lot of technology and energy community. This is quite important. We have, of course, Minalogic and Tenerrdis hosting the webinars today, but also actors in the academic sector, and Nordic Side was one of them. We have some other industries. We have administrations and institutes that are also active, and we have also all the grid operators that are important to us. Sometimes when we talk about the local energy distribution companies, we or people say that they are the small ones. Yes, we are small, but it's not because we are small that we are inefficient or we cannot do things. No, this is the little picture of Asterix, small but with different specificities, different strengths. And this coordination and this link with the different actors is, for me, completely essential. I'll give one example. We are working on a joint working group with the Enedis and the other DSOs, with the other small power DSOs, on the electrical vehicles and the impacts on the infrastructure of the grid. Of course, Enedis has much more people working on that, a team of 25 people on all over the country, whereas on our side we have maybe half a person or 1/3 of a person allocated to that full time. So the idea is not to compete on size, but to see what are the opportunities and the strengths of everyone. And for instance, that group was at the initiative of Enedis, because Enedis was also interested by what we can provide, meaning the link with the local politics, the link with the local authorities, that is maybe a bit stronger on our type of companies than it is on Enedis. And so we have this complementarity, and it's something that we will see in all our smart grid actions. First example of what is achievable as a local operator is what, of course, we don't have a research and development, a strong research and development department. But what we have is that we can test things, we can try things, we can implement things easily, quickly, and with a chain of command, chain of decision that is quite short. And we could quickly say, okay, let's try, let's learn by doing. And if the experiment is of interest, then we continue and take some advantage of it. And if it's not interesting, then okay, we tried, we have some learnings to take out from that, and then we stop the implementation. Citizen was one of them. Citizen Zen goes not only for the Zen part, but also for zero carbon energy. Zero carbon energy, and it was a joint endeavor between Grenoble and Amsterdam, going from housing, a lot of it, heating, cooling, smart grids, and the idea was to develop and test different projects on those two cities, and then to achieve a roadshow and to share those realizations, those results with other cities in Europe to foster their development and to see how we can each other take benefit of what the others could have done. Amsterdam worked on the vehicle to grid issue. They worked on the virtual power plant for flexibility on different houses connected. And on Grenoble side, we have been working on the setup of a PV plant with storage on a building just outside of Grenoble. And we have, and I see that there is a small mistake on the sentence. There's a sentence that is written twice. So the PV plant with storage was 55 panels and a battery behind that to see how the building could be completely autonomous on his power consumption. Vivacité was another project we were working on, and we are still working to deploy that on a larger area than Grenoble. It's a collaborative energy data management for cities, for citizens. It includes power and gas, thanks to the smart metering, but also the idea was also to include water, wood, and central heating, the urban heating network that is also on Grenoble, also embedded on this. Okay, I see what has a smart meter on power and gas, but what can be a smart meter on wood? Well, of course, there is no smart meters on wood. The idea behind is to be able to give the citizens the ability to follow their energy consumptions, whatever it is, even the ones who have wood as a primary or secondary source of energy. And then so they can follow their own consumption to be able to act on it, to be able to understand it first, then to act on it, and then to promote a better energy use for the neighborhood and the other participants. Another example I'll show on the idea of smart grid was about auto consumption. Auto consumption, we have more and more now with the smart meter deployment. We have more and more self auto consumption projects, but we had also a collective project, and it was actually the first autonomous building in France. And here again, what I want to stress is that it's the complementarity of the different actors that made that possible, that made that experiment possible. It has been initiated quite some years ago, 2014, by the city of Grenoble, by the constructor, so Bouygues Construction, by us. At that time, we were on GEG. We were not Green Alp as a subsidiary of GEG, but the GEG, Gaz Électricité Grenoble. Also, Grenoble Habitat, which is the social housing, because the idea behind is also the social housing. And to create that project, the idea was, okay, how can we start a demonstrator on different aspects, including smart grids and including a more global approach. So we have water, we have energy, we have well-being, we have waste, and we have social housing. All those aspects, how can we put that together with the will of everyone and start something from scratch and say, okay, let's put that as a demonstrator and then have learnings from this that we can then recreate somewhere else. For us, it was the first part on the self-consumption part, the first big implementation of the self-consumption part. It would include 50 or 60 users, and so the idea is to see also how this can change the way the company is approaching things, how this can change our way to deal with those projects, and how can we promote, how can we be as a grid operator, how can we be further promoter of any advanced solution. Oh, I see there's some noise issue, some sound issue. Ingrid? Well, Please don't hesitate to tell me.
Otherwise, I will alert you. But this is okay. Sometimes we don't understand that good, but it doesn't hamper the comprehension. If you can maybe speak up a bit.
Yeah, please tell me if I have.
Okay, this time we cannot hear you anymore. Okay. Okay, he is disconnected. Well, I hope he will be able to connect again. Maybe we can use this time if you have question, or if some of you want to share some consideration with us, then you can do it in the chat. Otherwise, okay, I see he's back. Okay, Youssef, if we can hear you, maybe you can turn off your camera.
Okay.
This will help the. Yeah, very good. Okay. Okay, we hear you. Go ahead.
Okay, I have changed connection, so I hope it is better like this.
Yeah, very good.
If there is anything I have to repeat, please don't hesitate to tell me about chat. I repeat directly.
So just because we are also a bit behind our schedule, yeah, if you can, well, within the 10 next minutes, that would be good to. Yeah.
Okay.
Thank you.
That's perfect. I mean, it's more enough. It is more than enough. That's perfect. Okay, so what I wanted to stress out here, you understood, is the collaboration about the different actors, and the idea is that, as Moina has stressed out in the introduction, not to oppose local versus global, but then to take into consideration all the participants that can be in such experiments, and to see what everyone can have what everyone can have as a specificity to add to a demonstration or to an experimentation. Last things about ABC, I had some figures, but maybe I can skip a bit. The idea here was a bottom-up approach and not a top-down, meaning that the building was engineered as being self-conception, and then the Grenoble Habitat was hiring inhabitants to say, okay, we have this project, and do you want to take part of it? And it has been a big turnout, 43 participants out of the first 50 inhabitants. The idea now for the other parts of the city is that how can we foster on the other side? How can we foster existing inhabitants to say, we inhabitants would like to go on more self-consumption projects, and we will build together a self-consumption project. So that's one of the challenges for later on the local experience and the local smart grid. To open up a bit the discussion, what can be those challenges for smaller company, and what's next? First, we need to carry on, and we have the will to carry on with testing, innovation, and setting up any project that we can have trials on that. We have been talking just earlier with Enedis on the smart metering deployment. We are just starting. We just started a couple of months ago our initial scale of deployment. We started in October. We have 10,000 meters deployed for the moment, out of 120,000 in power and 45 in gas. So it's just the beginning. And this project itself we have a lot of results, a lot of users, as we saw, as Elise had already explained. So I will not explain more. But it has also its roots on other projects we have been doing, other experiments we have been doing a couple of years ago, almost 10 years ago now. Gainless was a demonstrator project in 2005, 2016. And a lot of experiments taken from that project, from that demonstration for the first meters, first generation of meters, have now been used to build, to secure our current project, our current deployment project. And this is why we are doing any experiments and any demonstrators globally. It's also to be able to have those learnings that will be useful for us and also for all the industrial participants to those projects. One of the challenges about smart grids and the changes that are ongoing is how can we scale that? We go from small operations, okay, but how can we scale that and how can we foster that to a larger scale? And also, how can we put up some more robustness? We can start as tailor-made or maybe artisanal situations or constructions, but then we have to see how can we put that up with more robustness, with more scalability, so that we add comfort for both users and for both the technical operators of the grid and our colleagues. There's a big question, also already mentioned it, about the electrical vehicle, how the mobility of the electrical mobility will have effects on the grids. We have in Grenoble what it's called a ZFE, zone à faible émission, so a low emission zone. This has to be, this will be bigger and bigger in the city, meaning that thermal vehicles will be less and less allowed in the city. So what's the impact on the grid if in 10 years, 20 years, we have half the vehicles that are electrical, the other half that are a mix of hydrogen and natural gas? How will that be a constraint on the grid? And how will that be also an opportunity for the grid? And this is different if we consider Grenoble, which is a very urban and dense area. And if we consider the other districts that are more rural and sometimes mountain that we are operating into as well. On the challenges, we have been talking about the regulatory aspects with Guillaume earlier with the CRE. Those are also big challenges. How can we, for small distributors, small-scale distributors, how can we follow those regulatory evolutions? How can our economic model be strong enough? Because we have to maintain first and foremost our DSO activities. And of course, the IT part, it's written here as not to be underestimated, but I'd even rather say, whatever you do and you foresee on IT, you'd have, it is underestimated, and the impacts of IT are going more and more pregnant for the next year. Then the big question is how gas and power can be complementary. We have been discussing centralized and distributed architecture complementarity. We have been discussing global and local also complementarity. We should not forget the energy complementarity as well. So gas and power, also natural gas, but also hydrogen. And the idea behind it, not to forget what's the purpose we are serving with the smart grids globally. What is that purpose we serve? We have been talking about the more electrification, the better use for all the inhabitants, a better management for the system, for the whole system, for the grid. So if gas and the complementary power in gas can help that grid management, then it's not to be put aside, and you have also to take gas into consideration. And finally, regulatory definitions and evolutions. Storage is one of them. For the moment, DSOs are not allowed to be actors in storage. How will that be an evolution or not? How will storage can be used by DSOs, even if they're not operating themselves, but can be used by DSOs to help out their peak consumption. And then to reduce those peak consumption. So that's the questions that are still open for the future, and we have to keep in mind to see how can we go as a local company into this. So that's 8 out of the 10 minutes you gave me, and I'll stop here, and of course answer any precision question if something was not heard clearly, or any additional question, of course.
No, this is great. Thank you. Thanks a lot, Youssef. By the way, storage is a topic of our webinar on the 25th of March. So please connect then again. I don't see any question in the chat, but you raised a lot of interesting challenges. So if people want to react, no. Okay, maybe in the B2B meetings. Unfortunately, I have to leave you for an emergency, but my colleague will introduce you to the B2B and to the next webinars in our series. I personally thank you very much for your participation and also to the speakers. It was very rich and interesting to me, and I leave the floor to my colleague Bastien that will present you the next steps on this webinar series. Don't leave us, just 2 minutes, and see you later on the B2B and next Thursday. Bastien, thanks. Thank you very much.
Good morning, everyone. Is the quality of the sound enough for you? It is good? Hello, can you hear me?
Yes, it's okay, Bastien.
Okay, great. Thank you. Good morning. My name is Bastien, and indeed my colleague have to leave. So just a few minutes to explain you the rest of the process and also the rest of the program. So you will have a break, but then you have received a link to a website called Flux 50. This is a platform, pretty intuitive one, where you have to create your profile and then you can do matching and encounter and create your own agenda to discuss on a one-to-one basis. So if you haven't received it, please tell us on the chat, and we will send it to you. At the same time, while I'm explaining the rest of the program for the next coming weeks, maybe my colleague Natalie can write down the chat, the website for the platform that you should have all receive. We will give it to you in a few minutes. Also, so as you know, this is a 6-week program with a rhythm of 1 session each week. So it's happening on every Thursday, and the idea is to provide you an overview and a deep understanding of the smart grids and our regional ecosystem. So we have on the 4th of March the first session, today it's 11, we have the second, and we're coming for the third one next week. So for next week, we're having when smart grids connect with smart buildings in smart cities. So we have on speaker, we have Schneider Electric, XBA, Lancy, Sylphen, and also more digital companies like Probayes, Rayax, and Adonis. So it's the same principle. We'll spend the first 2 hours presenting innovative projects, and then we will have the B2B meetings. So it's very important for us, and I think it is for you, to be present during the full program, which is 6 weeks. We understand it can be pretty heavy to be present of each one of those, but it is important to create a full understanding of the smart grids and the ecosystem. So Ingrid just did it. You will find on the chat, you will find the link to the platform Flux 50. It's pretty intuitive, pretty simple to use. Traditional system, you create a profile, then you can request or you can receive demands for one-to-one basis. So this will happen starting from 11:50 or 12. So you still have half an hour to create your profile, to check on the catalog the profiles that are available to encounter and to meet, and then you just send a request. The rest will be done on the platform. So again, from the cluster Minalogic and the cluster Tenerrdis, thank you very much for your participation, and we're very keen to see you starting from 12 today and next week. Thank you.